All right, let's get right into it. You know, every time you turn on the faucet, you're actually witnessing the final scene of a really dramatic chemical play. I'm serious. It's a whole story with heroes, hidden dangers, and this tiny molecular battle that's fought just to keep our water safe. So today, we're going to pull back the curtain on this two-act play, the chemistry of clean water.
So the whole drama really kicks off with this one question. See, our water sources can be just teeming with invisible enemies. We're talking bacteria, viruses, all sorts of nasty pathogens that can make us super sick. So how in the world do you fight an enemy you can't even see?
Well, you bring in a hero, right? And for more than 100 years, our champion has been chlorine. It's powerful, it's effective, it gets the job done. But like any good hero in a great story, it's got a complicated side. A dangerous secret, actually, that we're about to uncover.
And that, of course, brings us to Act 1, where chlorine makes its grand entrance. This whole part of the story is all about chlorination, the first, absolutely critical step in making sure our water is safe to use and eventually return to the environment.
Now, you should know chlorine doesn't always show up wearing the same outfit. Sometimes it's a gas, sometimes it's a liquid, kind of like the bleach you have at home, and sometimes it's a solid, like in tablets or powder. But what's really cool is that no matter what form it takes, the second it hits the water, they all transform to carry out the exact same mission.
So it turns out the real hero of the story isn't exactly chlorine itself. It's this powerful compound it creates the moment it dissolves, hypochlorous acid, or HOCl. This is the true workhorse. This is the active ingredient that actually goes on the attack and neutralizes all those dangerous pathogens.
But here's the thing. Our hero's power, it isn't always at 100%. This chart here shows it perfectly. Its strength is massively dependent on the water's pH level. Just think of pH as a dimmer switch for its power. If the pH is between about 6 and 7.5, that switch is cranked all the way up, and you get tons of that powerful hypochlorous acid. But as the pH goes up, that switch starts to dim, and our hero transforms into a much, much weaker form.
And this, my friends, is where the plot really thickens. Because chlorine's amazing, heroic power to disinfect, well, it creates a whole new problem. A dilemma that water treatment engineers have to figure out every single day.
The issue is, wastewater isn't just pure H2O, right? It's more like a complex soup of all sorts of other stuff. And one of the most important other characters in our play is ammonia, which mostly comes from us, human and industrial waste. So when our hero, chlorine, meets ammonia, the whole story changes.
So instead of staying this super powerful free agent, our hero gets tied up. It reacts with the ammonia, and as you can see here, this creates a whole new set of compounds called chloramines. Now, they're also known as combined chlorine. They can still disinfect, but man, they are way slower and way less effective. To actually win the fight against pathogens, we have to get past this stage.
Okay, so this graph, the breakpoint curve, it looks a little intense, but it shows the entire battle unfolding. Just follow along with me. As we start adding chlorine, that's the line across the bottom, it immediately combines with ammonia, creating those weaker chloramines. But here's the wild part. To win, you have to add even more chlorine. See that big dip in the middle of the curve? That's the point where the extra chlorine is literally destroying the very chloramines it just created. It's kind of nuts. Only after all that ammonia is burned through do we finally hit the breakpoint. And whoosh, the curve shoots up. That's victory. That's when we finally get that powerful free chlorine residual we need.
So, great, we've won. The battle against pathogens is over, the water is safe for humans, but here's that dangerous secret we talked about. The exact same chemical we use to protect ourselves is actually toxic to fish and other aquatic life. We absolutely cannot just release this chlorinated water back into a river.
And that brings us to Act 2 of our play. The pathogens are gone, but now a whole new cast of characters has to come on stage to neutralize our hero. They have to make the water safe for the environment. This whole process is called dechlorination.
So, this neutralization job is handled by two main families of chemicals. The most common ones are the sulfur-based agents, but there are also non-sulfur agents, and they have some pretty unique tricks up their sleeves.
The big players in the sulfur-based family are things like sulfur dioxide, sodium sulfite, and sodium bisulfite. I mean, these are the real workhorses of dechlorination. Their job is simple, and they are incredibly fast. They just react with any leftover chlorine and poof, they turn it into harmless chloride ions, which you can pretty much just think of as salt in the water.
But among the non-sulfur agents,
one of them has a secret weapon, a special trick. It doesn't just solve the chlorine problem, it actually helps heal the water in another really important way. And that special agent is hydrogen peroxide. Check out this elegant trick. Not only does it neutralize the chlorine, but in the process of doing that, it actually releases pure oxygen back into the water. This is a huge environmental plus because it helps restore the dissolved oxygen that fish and other aquatic life need to breathe. It really gives that river or stream a much healthier start.
So as the curtain starts to fall, we can see that cleaning our water isn't just about one single heroic act. It's this carefully choreographed, really delicate final balancing act.
What we've really been watching is a performance with two vital goals. Act 1, chlorination, protects us, public health, by getting rid of dangerous pathogens. You get that wrong, people get sick. Then Act 2, dechlorination, protects the environment by neutralizing the very chemical that just saved us. You get that wrong, and the river life suffers. It's a total high-wire act.
So really, it all boils down to the number 2. It's this pair of actions, right? This addition and then this subtraction. That's what forms the foundation of modern water treatment. One just can't exist safely without the other. It's a perfect chemical partnership.
And all of this leaves us with a final thought. This complex, completely invisible ballet of molecules is happening constantly, all around us, just to provide something we totally take for granted, a clean glass of water and a healthy river. It really makes you wonder, doesn't it? What other invisible chemical reactions are out there protecting you right now in your everyday life?